Hi everyone, welcome back. So in the last lecture, we looked at the dyadic Green's function and we saw how we can go directly from currents to fields. Today we'll establish basically how those currents are computed numerically, right? So essentially we'll develop an integral equation and then we'll solve that integral equation using a technique known as method of moments. Okay, so before we do that, we need to introduce one theorem, which is called extinction theorem, that will help us make the connection between a given electric field and its current distribution, and we'll see why that connection will be important to establish the integral equation. Okay, so the theorem is called Wald-Oseen extinction theorem. Okay, so we'll start with this. Okay, so if you recall earlier in the class when we did wave matter interactions, we said that, given if I have a dielectric medium, some dielectric, right? It has some epsilon and mu, let's just say mu naught. And I have an incident field coming in. So let's say I have an incident field. So what is the incident field? The incident field is the field in space without this medium. Okay. Or you can think of it as a plane wave that's coming in from this direction. If you don't know what a plane wave is, just think of it as some incident field coming in from that direction, or something that exists in space without the medium. And once I introduce the medium, then inside the medium you have now a total field, right, which depends on epsilon and mu and the kind of material properties, right? So outside is epsilon naught mu naught. Maybe I should use a different color for outside just to be consistent. So here is free space, and here we have a medium. And when we did wave matter interactions, we showed that this is equivalent to having the incident field everywhere in space, right? Plus a scatter, instead of the medium, I can replace the medium with just polarization currents, right? So I have my total field, A total. And here again, I have epsilon naught and mu naught now, free space. So I have epsilon naught, mu naught, and the current in this location. So instead of the material, I have to place a polarization current JP, right? Where JP is equal to minus I omega epsilon naught chi E times E total. Right? JP is a function of E total. It depends on E total, not on the incident field. Right? It's not a causal relationship. It's not like the incident field creates JP. Yes, it does create JP, but the total steady state relationship is between JP and E total, not between JP and E incident. Right? But the problem with that, of course, is that JP is unknown and E total is also unknown because they depend on each other. Right? There's like this interrelationship. So we can't solve for either of them from just one equation. So to really solve JP or E total, you need another equation that relates them. And that equation will be given by the extinction theorem. Okay? Okay. There's another issue with this, which is that when I have an incident field, this one is at lambda naught, at some wavelength lambda naught. Inside the medium, you have E total, which is at lambda, which is not at lambda naught, right? Because inside the medium, K is omega square root of mu naught epsilon, whereas here, K naught, which is omega square root of mu naught epsilon naught, right? So I had an incident field out here, and here the field became the total field. Here you have an incident field, let's say it's coming in from this side, but there is no material here to scatter. So there should also be an incident field in here, right? But what happened to that? Because now we know that if this incident field was here, it should have a wavelength of lambda naught. So the extinction theorem basically says that JP forms in such a way that it cancels exactly the field inside this medium that has a wavelength lambda naught and only has a field which has a wavelength lambda, which is this E total. Okay, so if we write that in words, it says that E scattered is defined as, so earlier we said E scattered is kind of E total minus E incident, but that's a consequence of the extinction theorem. It's actually defined as the field generated by these polarization currents. And in terms of the Diodes-Green's function, dV prime. And extinction theorem basically says that this scattered field has two components, E total and E incident. So that when you add the scattered field, which is produced by JP, to the incident field exactly cancels everywhere because this is a point equation, right? It's a point form. It's a function of space, so it cancels everywhere, and you're only left with E total. And it also says that E total satisfies this wave equation. Minus K square E total equal to 0. Right? Which is the source-free wave equation in this case. Right? So in this case, there are no sources, it's just material. So E total should satisfy that wave equation in here. Right? Where this K is omega square root of mu naught epsilon. It's not the free space K. So what we're saying is that these polarization currents essentially radiate some field. That radiation produces E total and minus E scattered, which cancels exactly, minus E incident, which cancels exactly E incident here. And the total field that's left over after the cancellation is the same total field as this one, because it satisfies the same wave equation inside this medium. Okay? This total field also satisfies the wave equation, which is curl of E total minus, right? Yeah. So it's curl of E total minus K naught square E total equal to JP, or whatever the factor is, the mu JP, I guess, mu naught JP. And the reason behind that is that that wave equation is the valid wave equation for the field here with a source. But if you don't have source, if you are considering the source-free case, then it satisfies the left-hand side. Okay, so hopefully that makes sense. We're saying scattered field is produced by JP, has two components. This component cancels the incident field exactly. What is left over satisfies this wave equation. So it establishes a relationship between these two cases. And now we have a second relationship between the total field and the current, right? Because once I substitute this in there, once I substitute this in here, then you have a relationship between E total and JP. Okay? So with this relationship and this relationship, we can solve them because then you have two unknowns and two equations. Okay, so before we do that, I want to actually prove this. I can also mention that if I have a metal instead of a dielectric, then you can replace the metal with just the surface currents, Js, that are induced everywhere on the surface. And that produces a scattered field, which cancels the total field inside, which cancels the incident field inside. So in this case, you had an incident field, came in, you had incident field in here. Now the field scattered by the surface currents alone cancel completely the incident field inside. And there is no total field inside, we know that already. Right? So essentially, E scattered is minus E incident inside the medium for a metal, right? And outside the medium, of course, the scattered field exists as well, but inside the medium, it cancels exactly, right? So one way to think about it is that the polarization or the induced currents that are produced in such a way so as to cancel the incident field, and at the same time they produce whatever scattered field outside. Okay. Okay, so let's quickly prove this theorem before we move on to applying it. So maybe I'll do it in a new page. Proof. Okay, so we essentially want to show that if I decompose the scattered field into E total minus E incident, then substituting that E total using the scattered integral, which you can show that it satisfies the free space wave equation with K. That's what we want to do, right? So basically I'm saying that E scattered is equal to E total minus E incident. This is the decomposition I make. Then I want to show that this satisfies the wave equation with K, free space wave equation with K. Okay, so this is also equal to I omega mu volume integral G Jp dv prime. Right, so another way to write this is E total is equal to E incident plus A naught square IE, maybe I should write that out explicitly, um, plus I omega mu volume integral times Jp, but we know Jp is nothing but minus I omega epsilon naught IE E total. That was the first relationship between the two of them that we had from the wave matter interactions, so polarization currents. And now I have basically I times minus I is 1. I have omega square mu naught epsilon naught. This should be mu naught. So that's just k square or k naught square. Right? So this gives me E total is equal to E incident plus k naught square IE volume integral Faraday-Green's function times E total. I'll instead use dr prime instead of dv prime. Just it's a difference of notation. Doesn't really change anything. So this is known as the electric field integral equation. Okay. Why is that? Because you have an unknown quantity, which is the electric field, inside and outside the integral. And so that's what an integral equation is when you have an unknown quantity inside an integral and you want to solve for it, right? It's not an integral, it's an integral equation. Okay, so hopefully you've maybe seen that before, or if not, you can quickly look up what integral equations are. This is an example of it. Okay, so before we solve this, we want to use it in the proof of extinction theorem. So I'll define an operator, L, as the wave equation operator. Minus k naught square. Okay, so basically L of ek or L of E essentially means the wave equation V equal to 0. That's the wave equation. So this is an operator. Okay, and I'll apply this operator on both sides. So I apply it to this equation essentially. What do I get then? I have L of E total, the left hand side, plus L of E incident plus k naught square high E volume integral LG dotted with E total. I'm going to write it explicitly as R prime because the reason that L only applies on the Green's function is because only the Green's function is a function of R. Right? This is a function of R prime, and L is with respect to R vector. Right? These del operators are with respect to R. Okay, it's not with respect to R prime. That's why it doesn't act on this. It only acts on this. Okay, so now we can make some simplifications. This, before I do that, let's take here, this should be equal to. Okay, so this is nothing but 0, right? Because we defined the incident field as a field everywhere in free space, so it satisfies the free space wave equation. And this is I matrix times delta R minus R prime. That's the definition of the Diodio-Green's function. Right? It satisfies the wave equation with this delta function on the right. Okay, so essentially the right hand side becomes, so this becomes A naught square chi E volume integral E total R prime times delta R minus R prime dr prime. But once you have a delta function inside an integral, then that does nothing. It just pulls out. This whole thing just becomes E total evaluated at R now, right? Because the delta function only fires when R equal to R prime. So it's essentially like changing this R prime to R. Okay, so doing that gives us what? Doing that gives us L of E total is equal to A naught square IE times E total. And that's exactly what we want, right? This means that curl of E total minus A naught square 1 plus chi E total is equal to 0. And this term here is K squared. Okay, that's what we wanted to prove. So that completes the proof. Okay. So essentially we've shown that E scattered can be represented as E total minus E incident. And we showed that from that you can actually get an integral equation. And then that solving this gives us the total field, which we haven't done yet. And that's what we want to do next. Okay, so let's jump into that. Okay. Integral equations. Especially today we'll look at the electric field integral equation and how to solve it numerically. Okay, so we have two equations relating E and J. So we have E total. I'll use a subscript total equal to I over omega epsilon naught chi E times J. And this was for dielectrics. It's a volumetric current everywhere in space. For PEC, the relationship between I and J, E and J is nothing but 0. We know that for a PEC, the total field is 0. Okay? So in general, I can write general. So this is the point relationship. At every point, this is true. E total is some Z matrix times JS. Right? Because we're essentially relating one vector to another vector. And we saw that two vectors essentially are related by a matrix. We know that, right? So I'll write it in general like this, ZS. Okay, so this matrix is relating the vector component of this with the vector component of this. So this is a 3 by 3 matrix in general. And of course, in this case, it's a diagonal matrix. In this case, it's a 0 matrix. Um, it's not even just diagonal, it's diagonal with just identity. It's just identity times this, right? Unless, of course, chi E is the matrix itself, in case of some anisotropy. Okay. In case of an impedance sheet or a metasurface, this would still be a matrix. This would be just a scalar, right? And that's kind of how impedance sheets are defined. But we'll just treat this general relationship for now. Okay, so given that, I can write the total as, so I have my integral equation, which is E total equal to E incident plus I omega mu, volume integral, Green's function r comma r prime, dot j r prime, dr prime. Right? And now I can substitute. So I'm writing an integral equation in terms of the current rather than the field. You can do it both ways, but typically it's more common to solve for the currents because for metals, for example, the currents would be only on the surface, right? So you don't have to solve a 3D problem, it will become a 2D problem. So that's the preference. Okay, so I take this, is this, and I write J as Zs times J. Okay, so I'll make this also a matrix for now. Okay, so to solve this, what we do is we expand Js in terms of a set of functions equal to 1 to n, in fn of r prime. Okay, so this is called a basis expansion. Basis expansion, right? And these are your basis functions. So hopefully you're familiar with what a basis is. So one basis is the Fourier basis. Another basis is the delta function basis. Essentially, it's a set of functions whose linear combination can make any other functions in that space. Let's say if I have a current distribution, I can express it as an expansion in terms of basis functions. Now, in reality, you would have to put an infinity here. Not sure why this is not erasing. Okay. Anyways, so usually you would put an infinity here. You need like an infinite number of them in order to make it work. But in our case, we are going to truncate it essentially. See if that works. Okay. Some bugs in this software. Anyways. Okay, so we want to use n number of them. So it would not be a perfect reconstruction because of that. So we approximate this. So one example is that, okay, let's just say I have some function like that. Right? I can write this as a summation of the Fourier basis, which is just harmonics. To call the Fourier series sometimes. Something like that, right? So those are all the Fourier, that's the Fourier basis. Another basis is the delta function basis, where you have delta functions, right, that make up your function. So of course, if you use delta functions or Fourier series for an arbitrary function j, you need to use an infinite number of them. But we are truncating it, which means we don't have an exact reconstruction, right? We only have a approximate reconstruction, and that's what we'll work with. Okay, so hopefully the basis expansion makes sense. So once I do this, then the left-hand side becomes Zs sigma n equal to 1 to n, in, which are the coefficients of each of these basis function, r prime, is equal to E incident, which is a known quantity, r plus I omega mu summation n equal to 1 to n, in, volume integral. Now the Green's function applies on these basis functions. Okay, this is a vector basis, not a scalar basis, because every basis function also needs to be a vector. So the sum of them makes up the original quantity, dr prime. So the nice thing about this equation now is that the only unknowns are in. We know what these basis functions are, so we can compute this integral in theory, right? We know what zs is. We only don't know what this is, right? Because zs is given by the material properties. So in is the only unknown. And essentially, we want to see how to solve that. Okay. How many unknowns are there? So there are n ins, right? N goes from 1 to n. So there are n of them. So we have one equation basically here, which is a function of space. And we have n unknowns. So there's a small mistake here. This should be function of just r. Okay. So essentially, we want to get n equations. So how do you do that? You can evaluate this at n number of points, which we'll label with the index m, where m equal to 1, 2, all the way up to n. Okay, so that gives us n equations, right? So on the left-hand side, I have zs times summation n equal to 1 to n, in fn rm is equal to E incident evaluated at Rm plus summation n equal to 1 to n in I omega mu volume integral G Rm R prime Fn vector R prime dr prime. Okay, so I can call this whole thing as a matrix Zmn. It's a function of m and n. I guess it's not a matrix. Zmn is one of the values, it's just a value. It's a vector, I guess, or just think of it as some kind of value in terms of m and n. Okay, it is a vector because you are evaluating it over the space, but that's a vector of x, y, z. So, okay, and then I'll call this Vm, okay, which is another value, it's a function of m. And this whole thing I will call as Wn. Okay. Okay, so what is Wm? So Wm now is Zs matrix times I vector. So actually, to avoid confusion, maybe I should not put double labels here, right? Because although this is maybe I'll call it something else. Okay, so let me clarify. So this is a 3 by 3 matrix, right? Whereas this, maybe I'll call as Z tilde rather than Z matrix. Right, this is not 3 by 3. This is an m by n matrix, right? Because this is a matrix basically. Oh, oops. this is nothing but a matrix, right? So if I have summation over n, and I have n of them, m of them, then I can write that as a matrix relationship, right? So on the left-hand side, I have z tilde times I vector is equal to, now this is also a vector, right? Vn, which is an n by 1 vector. This is also n by 1. And once again, I have this summation relationship. Oops, getting confused. Once I have the same summation relationship with the ZMN here is 3 by 1 vector, right? So I can write this as V vector plus Z tilde prime I. Okay? Where the elements of Z tilde prime are the ZMN. So putting things together, I can rearrange this as V equal to Z tilde minus Z tilde prime I. Yeah, and I'll call this as the Z matrix. Okay, so essentially we have V equal to Z I. Okay? Maybe I should explain this a little bit better. So if I have summation n equal to 1 to n, Zmn In, right, Vm, something like this, then this is nothing but a matrix equation, right? I have V1, V2, V3, V4, and so on is equal to Z 11 I1 Z 12 I2, so on. This would be Z21 I1 plus Z22 I2 plus so on, right? And that's nothing but a matrix relationship. So essentially, whenever you write something like this, it's like a matrix relationship. And that's what we have here, right? Of course, this matrix is relating vectors, so you can do it one component at a time if you like. And that gives you this traditional matrix relationship. Okay? So hopefully that was not too confusing. But what we've done is, by the basic idea was that we started with an expansion in terms of basis functions, so that the only unknowns are the coefficients, substituted that into our integral equation, and then we can reduce essentially that integral equation into a matrix equation. Okay, and so we can solve this right now for In. So now my In is equal to Z inverse V. And you can use your favorite matrix inverting software or toolbox to do that. Backslash in MATLAB is one example. But that's how you can solve for In. And once you have these INs, this I vector has these INs. Once you have the INs, you substitute them back into your basis expansion, and that gives you the current distribution. And once you have, of course, the current distribution, then you can find the field everywhere, because by extinction theorem, this current distribution exists in space. So you can use the free space Green's function to find the radiated field everywhere. And then add that to the incident field, and that gives you the total field everywhere. Okay. The problem with this, of course, is that this is not very accurate. Okay, so if you try to solve this, if you try to use this to find the scattering from a thin metal wire, what's the issue? Right? By evaluating this expression, this expression here, this integral, we've only evaluated this at certain points, r equal to Rm, not at all points. If it was evaluated at all points, essentially using a complete basis, then we would get an exact, solution. The problem, of course, is that the Z matrix would be too big. So it's essentially like trying to balance between accuracy and computational burden. And so we've essentially only enforced that equation, which enforces the boundary condition for the total field at certain discrete number of points. Between those points, if you solve for the total field using the current distribution only at those points, so let's say you only evaluated at these points the current. So on these points, the current will be exactly correct. And if you use that to find the field, then ideally, if this is a metallic object, then the field should be zero everywhere on the surface. But you will see that it might do something like this, right? So it satisfies the boundary condition of total field being zero only on those points, because only on those points the current is accurate. Everywhere else, the current doesn't really exist if you use a delta basis, right? So this is with a delta function basis. And that's really the problem, is that this is not very accurate unless you use a large number of points, right? So to solve this, people came up with a really cool trick, which is called the method of moments. Okay, so what's the idea, the big idea behind method of moments, right? So the big idea is that you go back. I'm going to make a copy of this. Okay, so we said that, okay, instead of evaluating, we saw that if you just evaluate this at specific points, that doesn't really give us what we want, right? R equal to Rm, because it basically need too many points to get a reasonably accurate solution. And that becomes too difficult. So instead, what we do is that instead of evaluating this at specific points, so going back to our example of, say, scattering from a thin metallic wire, instead of evaluating at specific points, I will evaluate it by averaging over certain region. Maybe that region gives me one integral, one relationship, another region like that, another region like that, another region like that, right? So by averaging over a certain region to get your n different equations, instead of evaluating at specific points, the idea is that the boundary condition would then be smoothed out or be satisfied in an average sense, right? So essentially, I want to evaluate it not at a specific point, but over maybe a region, or even over the whole region is one integral, use a different kind of average with a different weight over the whole region. That gives you another equation. So essentially, we need to extract n equations to complete our matrix that we can invert, right? At least n, because we have n different unknowns, INs. The idea is that I can extract those n different unknowns instead of taking points and evaluating this relationship. I evaluated over a weighted average of different regions. That's the big idea behind method of moments. Okay. So what is this weighted average? Right. So I will evaluate this relationship by taking a weighted average over another set of functions, Fm at RDR. Okay, so these are called your testing functions or weighting functions. Okay. On both sides. Okay, and there are, of course, n testing functions, and we want to kind of do this average on both sides. Now, if this testing function was a delta function, then we go back to our previous case, right? Which is this one. Okay, but of course it doesn't have to be a delta function. We saw that that doesn't really work very well, right? So instead of a delta function, maybe you want to use a different function, and we'll see what kind of functions we will use for the testing and basis functions at the end. But that's the big idea behind method of moments. Okay, so just for simplicity's sake, I'm going to call the left-hand side E total, which is what it is really, right? So once I apply this, then what do I get? I get volume integral over M E total at R dot Fm, so zero vector dot product at R dr is equal to volume integral over M E incident R dotted with Fm R dr plus summation n equal to 1 to n I I omega mu, put this in a box. You have two integrals now over two volumes. One volume over the testing function and one volume over the basis function. Fmr dot Green's function r comma r prime Fn of r prime dr prime dr. Okay. So now this I can write as my Zmn. This becomes my Vn. And this whole thing becomes my Wn. Okay. So essentially I get the same relationship again, which is W equal to V plus Z I. We can add a tilde here, fine. Right? And this essentially gives me the same thing, which is V equal to ZI. So we've reduced it to essentially amount to evaluating this, inverting this. Okay. So this is way more stable based on the choice of basis functions. And this is called your method of moments. Okay. So there are some practical considerations in evaluating these things. So what are these practical considerations, right? The first one is in the Zmn term, which is I omega mu Vn V Fm R dot G R comma R prime dot Fn R prime dr prime, right? Okay, since we're evaluating a current, R, let's say you're on the surface of a metal or inside the dielectric, and you want to evaluate this integral to find the current, which means you need to evaluate the observation point and the source point at the same point in some cases, right? So they will be essentially when R equal to R prime, you will have a singularity in the Green's function. Right, because we know that the Green's function is a function of the scalar Green's function, and that has a singularity when R equal to R prime. Okay? However, it is removable. It's a removable singularity. Right? And we'll see how to remove it in the next lecture. But just to give you an example, right, if I take the function sine x over x, right, if you plot this, it looks something like this. Right, of course, at x equal to 0, this is not defined, right? Because at x equal to 0, you have kind of 0 over 0. right? So what we do is that we define the sinc function as equal to sine x over x when x is not equal to 0, and we say it's equal to 1 when x is equal to 0. Because we know that the limiting behavior of sine x over x as x reaches 0 is equal to 1, right? You can take the Taylor expansion of that and you'll see that as x goes to 0, this is approximately equal to x. It's the small angle approximation of sine. That's essentially as x equal to 0, this and this cancel equally exactly, and you approach 1. But at 0, there is a singularity. So essentially what you can do is you can define a new function such that it's equal to 1 at x equal to 0 and sine x over x otherwise, and that gives you a continuous function. Continuous, smooth, differentiable, all of it. Right? It's a very nice, well-behaved function. So that's essentially an example of a removable singularity. So the idea is that you essentially take the limit and then see what value it's converging to, and then set that to be the value. This is just an example, and we'll see in the next lecture that you can in fact remove the singularity in the Green's function. Okay? Now, you can either do it analytically or you can do it using the principal value integral. Analytically is not always possible because you need to know what this Green's function is and what the basis functions are. It doesn't depend on the basis functions actually. It mostly depends only on the Green's function. You cannot always remove it basically. Because it also depends on what, actually it does depend on these basis functions, right? Because the singularity is being integrated over. So analytically, it's not always possible, but using a principal value, you can always do that. And we'll see that in the next lecture. Okay. Now, in terms of the choice of the basis functions, that's the second practical consideration. And testing functions. How do you choose these functions, right? Okay, so the typical approach, which is very popular, called Galerkin's method. And in this method, essentially the basis function and the testing function are chosen to be the same. Okay, so we use the same set of functions for both the basis and the testing. And that's what Galerkin's method is, and that's the most popular, shown to work well, and so on and so forth. Okay. How do you actually choose them? Kind of functions to use. So there are basically two categories, which are subdomain basis functions. And these are your delta functions. So you have Dirac delta, which amounts to what we did earlier. And when you do this, it's called point matching, because you're just choosing single points and matching the fields there. So essentially choosing Dirac delta basis functions under Galerkin's method is point matching, because you choose the same point for finding the field and also to test the field. So Dirac delta is 1. You could choose maybe pulse basis. Right? So pulse basis is something like that. Right? You choose an individual pulse. So if I have a current distribution, that's like that, then you're essentially breaking this up into pulses, which is similar to point matching. The only difference is that now you're averaging over a certain region. You're not choosing a single point. Right? So it's a little bit better. But of course, it leads to a discontinuous current. Right? And it's not easy to do this when you want to do 2D currents that are vectors. Right? So here, if you know the current distribution is only along one direction, let's say along the surface of, along a wire, then you can use this pulse basis, which is a scalar basis. Right? You just add a vector component, constant vector component to it. So scattering from thin wire, this is a decent option. Right? Another option is triangular basis. So it's a little bit better. So you're just kind of taking it one level of complexity at a time. It's a triangular basis. The nice thing about pulse basis is that, okay, once you put the pulse function in, since it's constant over that you only have to integrate the Green's function in that small region. You don't have to integrate the basis functions itself. So then you only have to deal with the singularity in the Green's function, right? So maybe I should explain that a little bit better. So if I put a pulse basis here, if I put a pulse basis here and here, then what does that do? That doesn't do anything. It just changes the volume integrals for each of the pulses to that region over which the pulse exists. And then this becomes 1. This becomes 1. And then you only have to integrate this Green's function over that pulse basis, over that domain, right? Over the support, it's called the support of the pulse basis, and that becomes easier. But once you make it triangular, then it's a little bit more complicated, right? But it's more accurate. Why is that? Because if you have a triangular function as your basis, then it's like doing linear interpolation. That's what triangular basis does. I have 3 different triangles like this. When I add them up, right, I get something like this. So you get a continuous function, but it's continuous, but the first derivative has discontinuities. Right? And that's the idea, is that it's one level better. And of course you can keep going. You can make it more and more complicated. But these are still subdomain cases. Okay, and then you can use like a truncated sinusoid. You can use, that's a truncated sinusoid. Right, so that gives you a slightly better maybe approximation. Okay. Okay. The other category are called entire basis functions. So entire basis means that the entire domain, I should say, not entire basis. Entire domain. So entire domain basis is basically a basis where each basis function exists over the entire domain. So one example is the Fourier basis, which is the Fourier series, and so on. So why is this useful? I mean, for example, the Fourier basis might be a great basis for a thin wire of a certain length, because we know current distribution on that wire would look something like a sinusoid, right? Based on how thin based on how long the wire is. So in this basis, you only need a few coefficients. You don't need a lot. So choosing the right basis can be quite an art, right? And that can simplify the problem a lot. It's something like data compression, right? When you use the wavelet basis or some kind of use the right basis, you can get very sparse representations of your signal, right? That's what compressed sensing kind of is. That's not what compressed sensing is, but anyways, it's the same idea. It's that choosing the right basis can give you a very sparse representation of your signal. So then your method of moments matrix can be sparse or small, and inverting it is easier. Okay, so Fourier series is one example of it. Okay, so before I close, I would like to say that in scattering problems where you have metals, where you have currents on the surface, the actual basis that most commercial solvers use is called the Rao, Wilton, Glisson basis, or the RWG basis. Okay, so I won't talk too much about this. Basically, it's a vector valued basis. So it's vector valued. It's something like triangular, not exactly. It's like a triangular basis on the surface of, on a surface. So it's a triangular basis like 2D version of that, and vector valued. And it works well with triangular meshes because of that, right? So it enforces the boundary condition on the current. So I should say that as well. It enforces current continuity automatically between the basis elements. And it is in fact a subdomain basis. So essentially you have like 2 triangles like that. And the current distribution on the edges flows this way, and then it flows through here, normally through this edge, and then on this edge again, it flows this way, this way. That's kind of what it looks like. Okay. All right. So if you're interested in learning a lot more about details of method of moments, I highly recommend a series of videos by Jordan Boudou on YouTube. I think his channel is called Lectures by Jordan Boudou. So I knew him when he was at Michigan. As a grad student, he was a postdoc. And I would say he's really a world expert on method of moments, you know. So he knows a lot about it. He has done a lot of research even in this area. So he has a very nice series of, I think, 5 or 6 videos where he gives you examples of using method of moments for scattering problems. So I highly recommend it. So in this video, I just wanted to kind of introduce the basic idea behind method of moments and how it's used to solve currents. But we haven't really delved into a lot of the detail. We just covered the basic ideas. Okay, so we'll stop here. Just to summarize, we discussed extinction theorem, how it's used to develop another equation between the total field and the current distribution. And then we used the proof, we looked at the proof of extinction. Then we saw how we can use that to establish an integral equation. And then we saw a numerical technique to convert an integral equation into a matrix equation. Then we also saw why that's not very stable by just doing point matching. And we saw how we can improve on that quite a bit using this technique called method of moments. And we looked at the equation, the integral equation in terms of method of moments and how that becomes a matrix equation. And we also looked at the basis functions, just a quick example and overview of different basis functions. And that's where we kind of concluded. Okay. All right. So hopefully you enjoyed that. Kind of a broad, quick overview of method of moments and integral equations. The next video, we'll look at how to take care of this singularity in the Green's function using principal value integrals. And we'll actually see how we can use this integral equation approach to solve for scattering from metals. So this was a very general discussion today, but we are more interested in scattering from metals, and that's a slightly different formulation. We just call the magnetic field integral equation, and we'll see why that's more stable and how that can be used to treat the singularity in the Green's function. Okay, thank you. See you in the next one.